we are to show that for a, n, m belonging to the set of integers, a raised to the power negative n is equal to 1 all over a raised to the power n. 1, 2, 3, 4, they are the laws of indices. We are to show them. We take solution. First, we are going to start by recalling this. We know if we have a raised to the power n, it is simply equal to a times a times, we have to multiply a by itself n times. That's what it means. N times. Next, n, if we have n, we can write n as, n belongs to the set of integers. We can write n as 1 minus 1 plus n. 1 minus 1 gives us 0. 0 plus n remains n. So nothing new has been done. Now, for us to get negative n, we are going to multiply both sides by negative 1. Negative 1 times n gives us negative n. So this will be equal to, we are going to multiply the right hand side by negative 1. Negative 1 times 1 minus 1 plus n. Next thing, we have to expand the bracket at the right hand side. This will simply be equal to negative 1 times 1 gives us negative 1. Negative 1 times negative 1 gives us positive 1. Next, negative 1 times positive n gives us negative n. This is equal to, I will bring the positive 1 in front. This will give us 1 minus 1 minus n, which is simply equal to 1. For these two terms, you'll see that negative 1 is common. So I'll factor out negative 1 minus 1 plus n. It is the same thing. Now the next thing, what we are going to do is we are going to take a raised to the power negative n. A raised to the power negative n will simply be equal to a raised to the power 1 minus 1 plus n. Such. The right hand side, this will simply be equal to, we are going to make use of the third property, which says that if you have a raised to the power n divided by a raised to the power m, it is equal to a raised to the power n minus m. We will see if we compare this. If you compare the right hand sides, n will be 1, our m will be 1 plus n. So this will simply be equal to, we are going back, this will give us a raised to the power 1 divided by a raised to the power 1 plus n. We know we can write it as such. We know a raised to the power 1 is simply a. So this will simply be a over a raised to the power 1 plus n. And this will simply be equal to a over, we know a raised to the power 1 plus n is the same as a times a raised to the power n, where a is a to the power 1. So in here at the denominator, we are making use of the second property, second law, which states that if you have e to the power n times e to the power m, it is equal to e raised to the power n plus m. So this will simply be equal to, if we simplify, you'll see that a will cancel a. We'll be left with 1 over e to the power n. Then we conclude, therefore, a raised to the power negative n is equal to 1 over a raised to the power n. We are done with the first one. We go now to 2i. For 2i, we have to show that a raised to the power n times a raised to the power m is equal to a raised to the power n plus m. This is what we have to show. For us to show it, it simply means we can take the left hand side and we show the right hand side, or we take the right hand side, we show the left hand side. So by making use of the left hand side, if you take a to the power n times a to the power m, it is simply equal to, we know a to the power n simply means take a times we multiply a by itself n times a times a times 3 dots times a. Here we multiply a by itself m times. If we take off these brackets, this will simply be equal to, you will see that we're multiplying a by itself n plus m times. A will appear n plus m times. So this will simply be equal to a times a times a times, we put 3 dots, times a. We are multiplying a by itself n plus m times. So if you write this in index form, it will simply be equal to a raised to the power, because we are multiplying a by itself, n plus m times, of which we are done. We conclude, therefore a raised to the power n times a raised to the power m is equal to a raised to the power n plus m. We go now to 3i. For 3i, we are to show that a raised to the power n divided by a raised to the power m is equal to a raised to the power n minus m. By making use of the left hand side, a raised to the power n divided by a raised to the power m, this will simply be equal to, we can write it as such, a to the power n all over e to the power m. This will simply be equal to e to the power n times 1 all over e to the power m. So by making use of the first property I, this will give us a raised to the power n times, this will give us a raised to the power negative m. Now by making use of the second property, this will simply be equal to a raised to the power n plus negative m, which will simply be equal to a raised to the power n minus m. We conclude, therefore a raised to the power n divided by a raised to the power m is equal to a raised to the power n minus m. Underline the result. Now we go to the last one, IV. We have to show that a raised to the power n, all this raised to the power m, is equal to a raised to the power n times m. By making use of the left hand side, we can show the right hand side. If we take a raised to the power n, all this raised to the power m, we know this will simply be equal to a raised to the power n times e raised to the power n times 3 dots times e raised to the power n m times, means you multiply e raised to the power n by itself m times. That's what it means. Now at this level, it is simply equal to, we know a to the power n simply means we have to multiply a by itself n times. Make use of our brackets, e times 3 dots times e n times. Times, just put the 3 dots, times e times 3 dots times e n times. Then we know we have to perform this product m times. So all this will be performed m times. So you see that we have to multiply e times 3 dots times e m times. This will simply be equal to e times e times e times 3 dots times e. You have to multiply this n times m times. So this will simply be equal to, now we have to write this in index form. You see that we are multiplying a by itself n times m times. So this will simply be equal to e raised to the power n times m. Then we conclude, therefore, e raised to the power n, all this raised to the power m, is equal to a raised to the power n times m. Presently, I'll give some few examples on how we apply these laws. Examples. How these laws are applied. We take for I, if you take for example 2 raised to the power 3 times 2 raised to the power 9 is simply equal to 2 raised to the power, we are going to add the powers, the bases are the same, 2 raised to the power 3 plus 9, which is simply equal to 2 raised to the power 12. We take 2i, we take 3 raised to the power 17 divided by 3 raised to the power 5. It will simply be equal to, in this case we are going to apply the third law. It will simply be equal to 3 raised to the power 17 minus 5, which is simply equal to 3 raised to the power 12. We take another example, 3. If we have 5 raised to the power 2, all this raised to the power 10, will simply be equal to 5 raised to the power 2 times 10, which is simply equal to 5 raised to the power 2 times 10 gives us 20. We take the next one, 4. We have 2 raised to the power negative 2 is simply equal to 1 all over 2 raised to the power 2, which is simply equal to 1 all over, we know 2 raised to the power 2 is as 2 times 2, which is 1 quarter. So these are some few examples demonstrating on how we apply those laws.